Yeah, so I guess I'm going to start. So, welcome. My name is Simon Mockery. I'm at Yale University in Physics and Applied Physics. And I'm going to talk to you today about the application of X-ray photon correlation spectroscopy to studies of soft condensed matter. And I'll explain to you how to do XPCS, X-ray photon correlation spectroscopy, is XPCS, and I'll show you a couple of examples of experiments that have been carried out, that we've carried out to characterize a couple of different systems using XPCS. And when I say characterize, I mean characterize the dynamics, the time-dependent behavior of soft condensed matter systems. So one of the examples that I'll show you concerns glasses, two different glass phases. And so the picture here on my slide shows two sort of walls of glass at Yale University. One of them is an old glass. That's this one here. This is kind of an old stained glass window, and that represents a glass phase that's well understood for a long time in soft condensed matter. And I'll also talk about a new glass, the so-called attractive glass phase. And so I have a nice spanking brand new building here that represents that new glass phase. So the first thing I thought I would do is talk a little bit about brightness and coherent X-ray beams, because a coherent X-ray beam or a partially coherent X-ray beam is essential if you're going to do an X-ray photon correlation spectroscopy experiment. And the intensity of your coherent beam, the number of coherent photons that you have in your beam, directly depends on the brightness of your X-ray source. And so X-ray photon correlation spectroscopy is a technique that really relies on very, very bright X-ray beams, such as are available at synchrotrons and third and fourth generation synchrotrons. Then I'll talk a little bit about XPCS studies of the dynamics of colloidal suspensions. And really the goal with this part of the presentation is to introduce you to the technique and sort of demonstrate to you how it works and so on. Then I'll talk about these two different kinds of glass and how we realize two different kinds of glass and what different behavior that they display. And that will run into this bit where we actually realize it in a colloidal suspension that's suspended in a binary liquid mixture, and it's actually the binary liquid mixture that allows us to tune the strength of an attractive interaction between the particles of the suspension, and that's how we go from one of these glass phases to another glass phase. XPCS can also be used to study the dynamics of polymers, and I'm going to talk a little bit about the dynamics of polymer membranes as realized in a couple of block copolymer systems where there are membranes that are built out of one kind of block suspended in a fluid, if you like, a liquid, if you like, of the other kind of block. And then at the very end, I'll just offer some conclusions and prospects for this technique of X-ray photon correlation spectroscopy. So first of all, let me try and explain XPCS to you. So XPCS is really the analog of quasi-elastic light scattering, photon correlation spectroscopy with optical photons, but now extended to, instead of using optical light, using X-ray photons. And what one does in an X-ray photon correlation spectroscopy experiment is that we measure the intensity autocorrelation function of the scattered X-ray intensity, And because we're using coherent X-rays, and I'll explain how to realize a coherent X-ray beam as a little bit later on. In fact, the X-ray beam, when it scatters off a disordered medium, gives rise to an X-ray speckle pattern, and the speckles will come and go as the configuration of the sample changes. And in that way, you can, if you can monitor somehow how, or the characteristic time upon which the speckle pattern varies, why then you can characterize those, because those times will reflect the characteristic times on which your sample is moving. And so that's the way you get access to the times, the characteristic times of your sample, by monitoring the characteristic times of the speckle pattern that your sample is giving rise to. Specifically, to do that characterization, we measure, we calculate from the data the intensity autocorrelation of the scattered X-ray intensity, and I'll explain a little bit a little bit later how we do that, and we measure that as a function of delay time and as a function of the scattering wave vector. The intensity autocorrelation function we call G sub 2 of Q and T. It's a function of both the wave vector and the time, and it's related to the normalized intermediate scattering function that's very often measured in, for example, neutron spin echo experiments via this relationship specified here, namely the intensity autocorrelation function, this G sub 2, is 1 plus the square of the intermediate scattering function. So, as I'm sure you know, this is typically a very important quantity for any condensed matter system, and so one is almost always interested in measuring it. The trick with XPCS, the issue with XPCS, is whether there's a range of times and a range of wave vectors within which the intensity autocorrelation function and therefore the intermediate scattering function have some interesting behavior. And what that will mean, in fact, is that one is typically looking at fairly slow times, time scales these days sort of from the thousands of seconds actually down to perhaps a few milliseconds, maybe even a millisecond. But at the moment, we have to wait before we can go faster than that for more intense, brighter, I should say, X-ray sources, and there are a number of issues associated with that I'll talk about later on. So as I've stressed, to carry out XPCS experiments requires a partially coherent X-ray beam, and so I guess the next thing I want to do is talk a little bit about that aspect of thing. I guess there's a thing here. So the problem is that there are many fewer X-ray photons in beams from even third generation synchrotrons than from laser sources, and so that's one issue. The second issue is that the X-ray scattering cross-section is generally much smaller than the light scattering cross-section. And therefore, the signals that you get in an X-ray photon correlation spectroscopy experiment are generally much smaller than the signals that you get in a laser light scattering photon correlation spectroscopy experiment. And therefore, you really have to worry a great deal. You have to be very concerned with the signal-to-noise ratio in an X-ray photon correlation spectroscopy experiment. It's also important to worry about the possibility that your X-ray beam might possibly create some X-ray damage within your sample, and so consequently one can't be exposing samples for too long. So that's another thing that one has to deal with in these sorts of experiments. But on the plus side, you can access much smaller length scales than you can access with laser light scattering, and you can look at opaque and turbid materials, which you can't do with laser light scattering. Basically, almost everything is more or less transparent to X-rays, and so you can really look at whatever you want to, in fact. Yeah. So back onto the requirements for XPCS experiments, and where I'm going here is trying to explain how to get a coherent X-ray beam. So or why you need a coherent X-ray beam. So the first thing is that the source must be as brilliant as possible, which means high brilliance synchrotrons, such as the advanced photon source or NSLS2 when it turns on, and so on and so forth. The beamline optics, so that was that one. The beamline optics have to be sort of as perfect as possible. They mustn't screw up basically your X-ray beam. It has to uh, uh, keep the beam as coherent as possible as it proceeds down the beamline. And it's useful and helpful to study strongly scattering samples in a way that minimizes the X-ray damage as much as possible. So my first couple of examples, namely the colloidal suspensions that I'll talk about, they're actually pretty strongly scattering samples because the objects that are scattering are silica beads suspended in a liquid. So the diameter of the beads is roughly 0.4 microns, 0.3 microns. So they're fairly large, and the electron density difference between the beads and the suspending fluid is rather large too. Silica has a density of about 2, and the fluid has a density of about 1, and so the electron density difference is correspondingly large. The second example that I'll talk about, namely the polymer system, is actually relatively strongly scattering, but for an X-ray experiment, but significantly more weakly scattering than the colloidal suspension. And consequently, you have to collect data for longer. The signal to noise may not be as good. It isn't as good. Another aspect of the XPCS experiments that I'll describe to you, and I think basically any XPCS experiment, is to use an area detector, so that rather than collecting at a single point in space, you collect over as wide an angular range as possible. That's something that the neutron scatterers know how to do very well and have been doing for a very long time. I think in X-ray scattering circles, we still have something to learn about how to optimally collect from as wide an angular range as possible over as broad a range of wave vectors as possible. The final thing I wanted to mention is that it's very important to have a very stable synchrotron and a very stable beamline. Otherwise, you start to measure the time dependence of your beamline shaking rather than the time dependence of your sample. So as I've mentioned, these sorts of experiments are generally carried out, or can only really be carried out, at high brightness synchrotron type sources. And this is just a picture, I think, of the advanced photon source. And I think this is an artist's impression. It's kind of an old picture of the NSLS2. And this now exists in reality on Long Island. But the point I wanted to make with this slide is that the reason that these sorts of sources are desirable for X-ray photon correlation spectroscopy experiments is the fact that these sources are based upon these so-called undulator devices, which undulate the electron beam that runs around the synchrotron in such a way as to create a very intense, very directed source of X-rays at particular directions and at particular energies, depending on the gap between the two bits of the undulator. So this undulator is a permanent magnet structure that undulates the beam back and forth. Maybe you can just about see the wiggles represented by this red line here. But the electron beam wiggles back and forth, undulates back and forth, I should say. and creates a very intense X-ray beam. And this bottom slide here just shows you the intensity that's created, or the brightness, actually, the flux that's created as a function of X-ray energy. So in this case, for example, with this particular setting of the gap, there's a very, very intense beam with an X-ray energy of about 7 kilovolts here. And I guess there's a second harmonic that's pretty bright at about 15 or 14.5 kilovolts. So it's really these undulators that allow us to make these sorts of measurements. This just emphasizes that point, these various different, so this is various different brightness figures, brightness, brilliance, really the same thing, for various different synchrotron sources around the world. This is the experiments that I'll describe to you were carried out using APS undulator A. So that's to say corresponding to this curve here. A typical value for the brilliance is a few times 10 to the 18th. Over at the ESRF, it's a little higher, a few times 10 to the 19th or 20th or something like this. This is just a different synchrotron. I'm not sure whether it's the Swiss light source actually, or perhaps it's the ESRF. I apologize for not remembering that. So as I've mentioned, XPCS requires a partially transversely coherent beam, and that means that the wavefront that's hitting the sample should effectively be a plane wave as it comes into the sample, so that everywhere sees the same phase and scatters with the same phase off to the detector. And one can actually calculate the number of transversely coherent X-rays in the beam, which is sort of the number of useful X-rays for XPCS experiments. And that's the number that passes through an aperture that subtends the solid angle corresponding to the coherence lengths, which I call XC sub X and XC sub Y. So, so if you confine the sample to dimensions that are approximately XC sub X and XC sub Y, then effectively the synchrotron looks like a point source as far as the sample is concerned, and there's phase coherence across the sample, and everybody scatters in phase, and then what you'll see in your X-ray scattering pattern reflects the individual locations of scattering centers within the sample, and you'll be able to make measurements in a way that I'll describe. In any case, you could calculate the number of coherent photons. It's proportional to, or it's equal to the brilliance, that's B, which is really the number of photons per unit phase space of the X-ray beam, multiplied by the area of the source. So sigma X is the source size in the horizontal direction, sigma Y is the source size in the vertical direction. So this is the area of the source, multiplied by this solid angle, multiplied by this solid angle, which is the solid angle corresponding to these coherence lengths at the sample. So you're at the sample and you're looking back, then the range of angles, the range of solid angles looking back to the source is given by this thing. But then there's a relationship between the coherence lengths and the source size given by this. And so if you substitute in these expressions, excuse me, for the coherence lengths back into here, what you discover is that the number of coherent photons is proportional to, or is equal to, I should say, the brilliance multiplied by lambda squared and really nothing else. And so the number of useful photons, which is what this number n sub c is really directly related to the brilliance. And so in XPCS experiments, what we really care about, in fact, the only thing we really care about is what's the brilliance of the synchrotron. Okay. In fact, so I now have to take a glass of water. So what I was just talking about was the transverse coherence, there's also this idea of longitudinal coherence, which is the which is related to the optical path length difference between X-rays scattered from different parts of the sample, and that should be no more than a few times the longitudinal coherence length, which is lambda, the wavelength of the X-rays, multiplied by the energy spread of the X-rays. Typically, in the experiments that we do, we don't have to worry about this so much, because it's always the case for a monochromatic beam that the and for small angle scattering, I should say, which all of the examples I'll talk about correspond to the small angle scattering regime. So we tend to worry about this, have to worry about this less, because these lengths, which come from the size of the sample, are always much less than the longitudinal coherence length of the sample. Now, that is not true if you go to larger scattering angles than the ones that I'll describe today. But for what I'll describe today, it is true. So as I proceed, you'll see this quantity beta, which is like the speckle contrast, and I'll sort of explain. It's really how visible the speckles are, and I'll show you some speckles in a minute, some X-ray speckles. But what this formula tells you is simply that this quantity beta is related to the coherence area divided by the illuminated area. So L times M is, L and M are the dimensions of the beam on the sample, and so that's the area of the sample that's illuminated, and pi times this sigma x and sigma y are the effective coherence lengths in the x and the y directions. And so this speckle contrast is just the ratio of these two areas. If you add longitudinal coherence to the mix, then it becomes a ratio of the two volumes. The illuminated volume is on the bottom, and the coherence volume is on the top. So that's how coherence lengths enter into what the data look like. It turns out, in fact, that the signal to noise doesn't strongly depend on this quantity. You can get the same signal to noise by increasing the illuminated volume, and really the signal to noise just depends on the number of coherent photons. It's just exactly what your data looks like. I guess you're less susceptible to systematic errors if the speckle contrast, this beta quantity, is not too small. So here's just a picture of what, a couple of pictures of what an XPCS experiment looks like. So this is the APS, and the experiments are happening in, I think somewhere sort of over here, maybe down here. And there are a bunch of hutches, and this is a picture looking towards the synchrotron, towards the beam, and the beam is actually coming through this hole in the wall, and it proceeds through these, I think there's a monochromator there. There are certainly a number of slits here, and then the sample is actually here, and there are some slits in front of the sample that define the illuminated area of the sample, which therefore define the coherence, the lengths that you're looking at, L and M. So L and M are, let me go back. So L is let's say the length, the width of the beam, and M is the height of the beam. So L and M define the dimensions of the beam, and so there are slits right around here. This black thing, I think, is some slits that define those dimensions. So this is looking towards the synchrotron. If you turn around through sort of 90 degrees and maybe walk a couple of steps towards the synchrotron over to here, and then look back out towards the beamline, then this is what you see. This little tube here that I'm indicating with my arrows is the path of the X-ray beam. So it's sort of amusing that you have this kilometer-long, kilometer circumference synchrotron, and you have this little tube here that's sort of a centimeter in diameter that brings the X-ray beam to your sample. And then just before the sample, you have, which is these sort of black things, you have slits that aperture the beam down. Aperture the beam down. I'm doing something with my hands. That aperture the beam down to a few microns. So there's this sort of nice change in scales all the time. Anyway, the sample is in this can here, and this micron-sized or few micron-sized beam hits the sample and then is scattered and goes down this tube, this flight path tube here that's expanding to sort of accept the ever-widening scattered beam. And then at the end here, sort of where I'm pointing to now, is where the X-ray area detector is. So this is sort of what things look like. The length of this hutch is probably 6 or 8 meters in length from top to bottom, from back to front rather. And in this case, the flight path from here to about here is probably 3 meters in this particular experiment. So that's pretty large for X-ray experiments. Maybe it's not so large for neutron scattering experiments. So this is maybe a little clearer of a schematic of the beamline at the bottom. So the X-rays come in here. There's a monochromator here, which restricts the wavelength and therefore means that we don't have to worry about longitudinal coherence. The longitudinal coherence length of the beam is always long enough. There's a polished beryllium window, and it has to be polished to prevent the scratches on the surface of the beryllium window from degrading the coherence of the X-ray beam. And then there are a bunch of slits here, here, and here that define the beam size to be about 20 microns by 20 microns, and also remove any scattering that comes from the process of defining the beam to this small size. Then there's a sample whose temperature can be controlled through some range, and then the X-rays are scattered from the sample and then proceed to the X-ray detector that's sat up here somehow. Okay, so that's sort of the geometry. Oh yeah, here's this is sort of what I was saying before. This is our sample block, and if you look at the very, you see this little rectangular opening in the block. So this is a copper block, and there's an aluminum block that's mounted on it, and the hole in the aluminum block, this one here, is a hole to let the X-rays through. But if you look carefully, you can see that in that block vertically, there's a little capillary that's mounted. So that's a capillary tube that's got a diameter of about 0.7 microns, and that contains actually our colloidal samples of colloidal suspension, and their temperature is maintained by maintaining the temperature of these blocks as well as we can. Okay. So just to sort of give you a better picture of how these experiments are, sort of what these experiments rely on, I wanted to show you this picture of the scattering from an aerogel sample using the coherent X-rays that we make at 8ID, for example. 8ID is the beamline that we use at the APS. So really the only thing that's important for the point of view of this discussion is that an aerogel is a sort of a mesh, a disordered mesh of silica that scatters X-rays rather strongly. And if you were to carry out a conventional small angle X-ray scattering experiment, what you would see is shown in the plot down here that I'm indicating. So this is plotted as a function of wave vector. The intensity is plotted as a function of wave vector. And you can see that at small angles, sort of in this region, there's pretty strong scattering, which decreases as the wave vector increases. So what this small angle scattering looks like if you carry out an experiment at 8ID using partially coherent light is shown over here in this slide. Now, you might expect to see a circularly symmetric scattering pattern, and what you're seeing here is just a portion of that circularly symmetric pattern. So the scattering is larger, if you like, than the CCD detector that we're using in this particular case. So this is just a sort of the zero position is somewhere down here. We don't have anything, no scattering over here. The scattering at the sides doesn't go too far. But you can sort of see, if I trace it around, that this is actually circular, roughly speaking. But now the big difference between this pattern and what you might see using a lab source or a less coherent beam is that there are regions where the intensity is very large. So what we're representing things here on a false color intensity scale where the scattering is very weak, where it's dark blue, and it's very bright, where it's red. And so there are these, well, you can see that this scattering pattern is what's called speckled. There are regions, let's see, there's one here, let's say, where it's dark blue, but right next to it there's a region here where it's red. And so there are wild fluctuations in intensity for these neighboring points. These wild fluctuations in intensity have nothing to do with counting statistics. There's basically no noise within this pattern. What this pattern originates from is the fact that we're scattering coherently from some disordered object like this over here. And so the intensity at any particular spot depends on exactly how the scatterers in the sample are arranged and whether or not at a particular scattering wave vector those objects scatter in phase or out of phase. So where the scattering is rather weak, somewhere over here, they scatter out of phase. Where the scattering is rather strong, oh, I hit it right on, they're scattering in phase. So this is a sort of very characteristic of a coherent scattering is the presence of speckle. And if the sample is static, like an X-ray, like an aerogel is static, why then the corresponding speckle pattern will be static. But if the sample is moving, why then the speckle pattern will move. And if you can characterize how quickly the speckle pattern is moving, why then that tells you how quickly the sample is moving. So that really is the principle of X-ray photon correlation spectroscopy. This is just to say that one can sort of characterize the statistics of speckle patterns such as the one I just showed. This, for example, this plot here shows the distribution of intensities, and there's normalized by the intensity, but the point is that this is a very broad distribution of intensities, much broader than you would expect based on anything other than this sort of speckle idea. And the line here is a theoretical expectation based on the beamline configuration. You can also calculate what you expect for the speckle contrast, that beta that I mentioned before. That's more or less what you expect for the beamline configuration. And in fact, you can even calculate the size of the speckles, and again, it's more or less what you expect. This particular experiment used what's called pink beam, which is not perfectly monochromatic, and therefore the speckles are elongated in the radial direction, corresponding to different wavelengths in the radial direction, scattering at different radial positions. In any case, the point is that we sort of understand what we're getting, and it's what we expect to be getting. Okay, this is just a reprise of everything I've said earlier. We have to have a brilliant source. The beamline optics have to preserve the brilliance. We have to use strongly scattering samples, or it's very helpful to use strongly scattering samples. We basically need X-ray area detectors, and beamline stability is very important. Just to touch again on the idea of area detectors, you can write down the signal-to-noise ratio using a CCD detector or using a point detector, which is the way X-ray experiments were done when I was younger. There's a huge gain to be gotten from using an area detector, basically because of this factor square root of n sub p, the square root of the number of pixels. For typical area detectors, there can be 1,000,000 pixels, and so the signal to noise can be increased by a factor of 1,000 compared to a point detector. The only problem with area detectors is that they tend not to be fast. You can only read them out so fast. The experiments that I'll describe to you today, some of those experiments were done at 500 hertz. Some of them were done at 62 hertz frame rate. So that's to say, at 62 hertz frame rate, you get one image every 16 milliseconds or something like this. And that limits the fastest time that you can characterize. If you collect data, if you read out data every 16 milliseconds, it's clear that you can't resolve processes that are occurring on faster timescales, on 1 millisecond timescales or 1 microsecond timescales. You're limited to looking at processes that are occurring on 16 millisecond timescales. This is the area detector that we use. It's actually no longer made, but it's still in operation at APS. The point I wanted to make with this slide is that the fastest it reads out is 62 hertz full frame. So you can read out 1,000,000 pixels once every 16 milliseconds. You can read out a fewer number of pixels faster. So for example, you can read out a 1/16th frame, so that's 1,000,000 divided by 16 pixels, whatever that is, 60,000, 64,000 pixels at 500 hertz. And so if you indeed have a strongly scattering sample, this detector allows you to go to 2 millisecond time resolution, let's say. Like I said, this is actually a 10-year-old detector at this point, maybe 12 years old at this point. And one of the challenges for XPCS is to get faster detectors that are efficient. They have a high quantum efficiency. They detect as many X-ray photons that impinge upon them as possible, and that cover as large a area of angular space as possible. The more of angular space, the more of the scattering that you collect, the better your signal to noise will be. And at the same time, in XPCS experiments, you typically like to at least, if not completely, then partially resolve speckles to avoid systematic errors associated with, well, is there or is there not a speckle contrast. You'd like to have a non-zero speckle contrast, 10% or 20%, let's say, and that means that the pixel size of your area detector can't be too large. If it's too large, you'll average over too many speckles. Your contrast will be small, and you risk having systematic errors that you don't want. Okay, so now so that was sort of my introduction to the technique, and let me just proceed by describing sort of a proof of principle experiments that characterizes the dynamics of a colloidal suspension. The colloidal suspensions that I'll talk about are still in a fluid phase, so the particles will not be at this point so closely packed that the suspension is trying to form a glassy phase, but they're still moving around, but they're certainly noticing the presence of each other. So over here, I just have a picture of the sort of system that we're looking at. This is a confocal microscopy image, and it just shows you that there are a whole bunch of little spheres fairly closely packed together, and so that's really what we're looking at. What that looks like in a typical small angle scattering X-ray experiment with an incoherent beam might be something like what's shown over in this slide here. Again, I'm showing a fraction of what would be a circularly symmetric scattering profile. If I was to have a larger detector, everything here would be circles. What you're seeing here is regions where the scattering is rather weak, regions where the scattering is higher, higher still, higher, even higher, and then very strong. And what you can do with data like this is one can average the intensity around rings. So I go around a ring like this, adding up all of the intensities, and then plot as a function of the magnitude of the wave vector. So I plot as I go out, and when I do that, I'll get data that looks like what's shown here. So what you see here is the azimuthally averaged small angle scattering profiles for a number of different colloidal suspensions with different volume fractions. So this is a volume fraction of 2.7%, and that corresponds to this profile here. And at 2.7%, the particles are fairly widely separated, and so there are not at 2.7% very significant interparticle correlations. And so this intensity profile at 2.7% actually comes from individual particles. It's the particle form factor of individual particles. They're little spherical particles, and so that's what these little dips and bumps are here. That's the form factor of spheres. They're slightly polydispersed. There's a distribution of sphere radii, and therefore the dips don't go down to zero, but they're filled in, corresponding to the distribution of different sized particles. Now, what you can see when you increase the volume fraction is that although some of these bumps and dips remain more or less the same shape as you increase the volume fraction, there's clearly a peak that somehow starts off over here, moves here, and then here and here as you increase the volume fraction. And so what this peak is the liquid structure factor peak of this colloidal liquid. And to isolate the structure factor, that is to say, the effect of correlations between particles, you can divide the measured intensity at the higher volume fractions by the measured intensity at the lowest volume fraction to then get at least an approximation, and probably a pretty good approximation, of the structure factor of the colloidal liquid. And that's been done over here, and that's what it looks like. At the highest volume fraction, you have a rather prominent, sharp peak here. Notice this is a log scale, so that sort of tends to conceal the sharpness of this feature. But this feature is relatively sharp at high volume fractions, and it's relatively broad at lower volume fractions. This is 13%. This is 52% volume fraction. So this is what we're scattering from, a suspension of fairly densely packed spheres whose volume fraction we can actually change and make measurements at different volume fractions. So let me contrast now this scattering profile, which is from an incoherent source, and this profile, which is now from a coherent source with just a 150 milliseconds exposure. So what you can see here is that this colloidal suspension appears speckled. So there are regions red where the intensity is very high, fairly close to regions where, let's say, green, where the intensity is much lower. So this is what is a partially coherent pattern, and consequently there's a speckle pattern. The reason, and this is sort of a very sluggish liquid that we're looking at here, it turns out, and so the reason that we actually can see a speckle pattern at all is because 150 milliseconds is not long enough for it to have moved significantly, for the particles in the suspension to have moved significantly, and so on this time scale they appear more or less static. You therefore have a speckle pattern. They are more or less static, and you therefore see a speckle pattern. So now I want to show you a movie, and this is a movie of a more dynamic sample. So the volume fraction is much less. The sample is quite liquid. And what I'm going to show you is, if you wait a minute, just a little piece of this ring. So this ring is like this, and the next thing is just a little piece of this ring, maybe a little slice going from here to here to here, here. So we're collecting the strongest part of the intensity, and we're just going to watch it as a function of time, but we've actually slowed things down a factor of 30. We're taking data at 500 Hertz. So if you could play the movie now, that would be great, and I'll just talk through the movie when it's playing. Yeah, so this is what XPCS data from a strongly scattering sample looks like. What you see on the screen is a bunch of bright patches, and if you focus on a bright patch for a moment, what you'll see is that it sort of stays there for a little while, but then it disappears, and you go to another one and that stays there for a little while and then it disappears. So what you're seeing is when something appears, that's a birth of a density fluctuation that just has the right spacing of particles to give rise to scattering at that particular space, that particular place on the detector. That lives for a little while, and then it disappears as that density fluctuation dissipates, relaxes, disappears. So what we can do now is we can characterize the time scales for these things to live. Basically, we measure how long these bright patches live, and the way that we do that is using, and we calculate from data exactly like this, the intensity autocorrelation function pixel by pixel. So we take a pixel, we measure its intensity as a function of time, we autocorrelate that intensity as a function of time for that pixel, and then we add to that all of the other pixels at the same wave vector, and in this way we build up the wave vector dependent intensity autocorrelation function. So I think we can stop the movie now, and I'll show you what those autocorrelation functions look like. So let me go forward. Yeah, to this one. And so calculating that autocorrelation function pixel by pixel, averaging together all of the pixels at the same wave vector, you get data like this. This corresponds to a volume fraction of 0.28, where things are still pretty mobile. This is actually a slightly different system than the one I showed you the movie from, but the ones from the movie look very similar to this. This is an exponential relaxation at several different wave vectors. If we look at the from data like this, you can deduce the time scale, right? This one is the time scale is decaying. If I read down in about maybe 5 seconds, this one is decaying in about 1 second. So you can determine the time scale for different wave vectors in this way. And if you plot the time scale, and I've plotted it in a peculiar way here as d0, which is the diffusion coefficient according to the Stokes-Einstein relation, divided by ds, and ds is given by this expression here, so it's the time scale that we measure multiplied by q squared. So really, these data, which are plotted as the squares, I think, are those squares? Yeah, I think they're squares. The squares and the red line, those are effectively time scales, relaxation times, and they're compared actually to the same structure factors that I showed you previously, which are these circles and blue lines. And what you can see here clearly, so as you increase the volume fraction from 13% up to 52%, you can see that the peak sharpens, which indeed corresponds to the suspension showing longer range order. It doesn't show long range, doesn't show full, true, long range order, but the extent of the ordering is definitely increasing as you increase the volume fraction. But what you can see is that there's a, if I look at this relaxation time, there's a peak in the relaxation time at the same place that there's a peak in the static scattering function. And what that tells you is that particularly stable, particularly favorable low free energy fluctuations, which is why there's a peak at that particular wave vector. So if there's a lot of fluctuations at a particular wave vector, that tells you that those fluctuations have a low free energy. The fact that there's a peak at the same, there's a peak in the time constant at the same wave vector, tells you that those fluctuations not only have a low free energy, but they're also long-lived. And that's actually a manifestation of de Gennes narrowing, which is known in atomic systems and in many systems. In fact, the lines in this plot are theoretical predictions, both for the static structure factor in the case of the blue lines, and this quantity d over ds in the case of the red lines, for hard spheres. And so, as you can see, we're more or less getting what we expect to see. And so the conclusion is that XPCS is working. So I think maybe I should stop for a minute, since I'm going slower than I thought for a few questions. I don't know if anybody has any questions. If anybody does have questions, maybe I can answer them now. So Ming asked whether the increasing volume fraction made the suspension more ordered. And the answer is yes. And the way that we know that is because the peak is getting sharper as the volume fraction is increasing. I've persuaded you that this technique, X-ray photon correlation spectroscopy, works. And now I'd like to go on to talk about a couple of examples. And the first example concerns phases or colloidal suspensions that realize phases that are glassy, more glassy than the phases that I've talked about previously. And so higher volume fractions, but also an attractive interaction between particles. What I want to do is show you this phase diagram, theoretically predicted phase diagram. So this is the phase diagram of predicted for a colloidal suspension with attractive interactions between the particles that can be tuned. So I'm looking at this phase diagram as a function of two parameters. The first one along the bottom is the volume fraction phi of the suspension. And the one up here along the vertical direction is the reduced temperature. So that's to say the temperature divided by the interaction strength, it's an attractive interaction. So when the temperature is very low down here, there's effectively a very strong attraction between particles. And in this regime, at least down below this line here, one is sort of familiar with what goes on. What goes on is that particles stick together and one sees these diffusion-limited aggregates. Things are sort of understood here, but you certainly get a frozen glassy phase because in these diffusion-limited aggregates, the particles just are stuck together and completely immovable. The other part of the phase diagram that is sort of understood for a long time is up here. At high temperatures, that's to say low interaction strength, where you can basically ignore interactions and you have effectively a hard sphere glass. And the behavior of a hard sphere glass has been studied for a long time and is sort of understood. The region down here, where you have relatively high density but relatively strong interactions between particles, also has been less well understood. And it's investigating what happens in this region over here, where there are attractive interactions, but not so attractive that you completely are frozen, at least not at all, not under all conditions. So I'm going to skip that since I'm running out of time. I'm going to tell you about the system that we're studying. And it's actually a system of silica spheres in water-lutidine. And we picked this particular system because it's been known for a while that, since the 1980s in fact, that if you adjust the temperature to be close to the consolate point, that's to say the point at which these two liquids, water and lutidine, unmix, if you adjust the temperature to a temperature below that phase separation, so these two materials have an inverted coexistence curve, so this is up here, at high temperatures they're phase separated, at low temperatures they're mixed. Anyway, somewhere down in this region here, in the one-phase region, but close to the consolate point, the critical point at which they're going to start to demix, there's an attractive interaction between the particles of silica that are suspended in this mixture. So what you can do is you can start at low temperatures where there's no attractive interaction, and then you can crank up the temperature, as I'm sort of indicating with my little arrow, and in that way you can increase the attractive interaction between these particles and tune the strength of that attractive interaction in a very convenient fashion. And so that's what we've done in the experiment that I'm going to describe to you. One way to see that is through the static structure factor. So as you increase the temp, so this is the lowest temperature, that's to say the weakest attraction. You have a scattering that looks pretty much like a hard sphere, what you expect to get from hard spheres. But as you raise the temperature and you increase the attraction, you start to increase the scattering at very low wave vectors. So the scattering at low wave vectors here is much higher than here. The peak gets broader than here. The peak here at high temperatures is broader than here. All of these things tell you that there are attractive interactions between the particles that are turning on. And in fact, you can measure the strength of that attractive interaction. So this is the strength of that attraction as a function of temperature. And we have data here from 3 different runs. Here's one run, here's another run, here's a third run. And the reason different runs are different is because we believe there's a differential evaporation of the 2 components of the fluid. And so the phase transition temperature shifts slightly from one run to the next run. But we're just going to be plotting things as a function of this interaction strength parameter. And so hopefully that won't affect the results too much. Okay, so now I have a pop quiz for you. So basically, if I go back to my phase diagram here, what I have in this region is a glassy phase, and what I have in this region is a fluid phase. And in our particular realization, we go from one phase to another by changing the interaction strength. We increase the interaction strength by decreasing the temperature in our system. In this case, it's you decrease the I got to get this right. You increase the interaction strength in our system by increasing the temperature. In the theoretical case, you increase the interaction strength by decreasing the temperature. So you go from here, a fluid phase, down to here, and you should go from a liquid to a glass. So what I want to do now is show you the 2 movies together. Could you show the 2 movies together? And one of them will be a liquid phase, and the other one will be a glassy phase. And based on what you see, the quiz for today is to decide which one is the liquid and which one is the glass. And so right now, okay, so they're both running now. And if you look at the one on the left, if you focus on a speckle, a bright spot, for a few minutes or a few moments, a few seconds, you'll actually see that it only lasts for a few moments and then it's gone. But if you look on the right-hand side and focus on a spot, actually what you'll see is that that spot kind of stays there. It gets dimmer sometimes and brighter and dimmer, but the spot always seems to sort of be there. And this is telling us that the sample on the right is a glassy phase. The speckles aren't moving. The speckles aren't changing in time. They're not disappearing in time. And so for the sample on the right, why then the sample is static. It's not moving. It's a glass. By contrast, on the left, the speckles are there for a minute, then they're gone, a new one appears, it's gone, and so on and so forth. So in this case, the sample is moving, and this therefore is a liquid. So hopefully you can see that, but this is sort of the basis, sort of directly in the data for the difference between a liquid and a glass. So can I have my PowerPoint back, please? So in just the same way that I described before, we calculate the intensity autocorrelation function pixel by pixel at average over all wave vectors that are equivalent to each other, and then plot these data as a function of time. So this is now looking at one particular wave vector for various different temperatures. And starting with the orange one, which is the lowest temperature, I'm cranking up the temperature. So I go from something that looks pretty glassy. It's glassy because I have this long plateau region where nothing is decaying. Maybe eventually after 100 seconds, it moves, and I don't want to discuss actually what happens at long times. So only look at these plots for times up to about 20 seconds. But there's this long plateau out to 20 or 30 seconds where there's little decay, and that tells you that there's a glassy phase here. And actually, an initial decay from a value of 1 down to a value that's less than 1 is characteristic of the old glass that I mentioned, a hard sphere glass that I mentioned previously. This particular data set doesn't have data at very early times because these data were taken at 62 Hertz. I think in a minute I'll show you data that was taken faster, and there are data down at shorter times. I hope so anyway. In any case, as you increase the temperature, which is in our case increasing the attraction strength, because we're going closer to the consulate point and therefore increasing the attraction strength. As I increase the attraction strength, somehow the plateau gets weaker and weaker and weaker. And by the time I've got to this green color, which is about 0.4 degrees hotter than the orange color, I'm actually decaying. I actually decay, the correlation function decays all the way to 0, indicating that now I don't have persistent correlations. I'm in now a liquid phase. And I now jump to this B. The data here in green is the same as the data here in green. And I keep on, so here I was increasing the temperature. I keep on increasing the temperature from here, but now I go this way. So this is sort of remarkable. You go from a glassy phase to a liquid phase, from that liquid phase back to a glassy phase. Okay. The character of this glassy phase is different from this phase here. So here I started off at a value of 1. I went down to a plateau value of about 0.4. Here I sort of have this very strange decay, which is a straight line in a logarithmic time scale. So this actually corresponds to a logarithmic behavior of the intermediate scattering function. And the slope of that logarithm gets less and less and less, and eventually by 36.6 degrees, I'm completely flat, so completely glassy at this point. This is just what I advertised before. I have now collected data that's faster, and so I actually go to 1, but you can see the same sort of phenomena. This is a slightly different run. I start off here, I increase the temperature, things get slower and slower. Here it doesn't go all the way into a liquid phase, but it sort of goes, it gets faster, but then it changes its mind, gets slower again. So this is lowest temperature, some intermediate temperature, same intermediate temperature, highest temperature again. So you can see the same sort of phenomenon is occurring. And I'm going to skip those fitting results, not very interesting. And the bottom line of this experiment is that you can sort of map the data that you observe, the behavior that you observe. So the green shows this so-called attractive glass, where the correlation function sort of looks like these red correlation functions, very flat with a value of 1 for a very long time, or possibly this slow logarithmic decay. So that's the green things, in this plot here. The red ones correspond to that original behavior I described, where it starts off at 1 and then drops to a value of about 0.4. That's what you expect for a hard sphere glass. And then in the middle of them, you see these this blue behavior where it becomes liquid in between this attractive glass and this repulsive glass over here. And that's sort of what you expect in this from this phase diagram. Here I start off in a repulsive glass over here, but if I just change the interaction strength, I can go into a liquid, but then I can change it some more, I can go into another glassy phase, a different glassy phase. So this experiment just seems to realize at least this sort of behavior that's seen here. Now, in the last few minutes, let me just mention that you can also apply X-ray photon correlation spectroscopy to polymer systems, which are much more weakly scattering than the colloidal systems that I've described to you. And so typically you have to collect a lot more data in terms of time, but you can nevertheless make measurements. So let me just sort of show you the sorts of some measurements that are possible. So I'm actually going to describe to you some measurements carried out on mixtures, blends, if you like, of a tri-block copolymer, polystyrene, polyethylene butylene, polystyrene. So it's a tri-block copolymer with 2 polystyrene end blocks and a ethylene butylene mid block. And as I'm sure you know, those 2 blocks don't like to be next to each other. And in fact, what happens is that depending on the amount of polystyrene that you have compared to the amount of ethylene butylene that you have, and what we do to change the amount of polystyrene is we dissolve this tri-block in a polystyrene homopolymer. And so one can think perhaps of the polystyrene homopolymer as being the solution that these amphiphilic molecules, PCEBs, are dissolved in. In any case, when there's not very much tri-block, these materials form sort of these large vesicles. When you increase the amount of tri-block, why then they form this so-called sponge phase where you can't tell the inside from the outside. Now, I'm going to just show you some data from some XPCS data from the vesicle phase. And since I see I'm running out of time, let me show you. Can we show this movie quickly? Oh, it's okay if I need more time to finish. Okay, I'll take a little more time. I'll try and speed up as much as I can. Just to sort of visualize what we're looking at here. So this is a simulation of a membrane, sort of a generic membrane whose fluctuations are controlled by its bending elasticity. And the idea is that the vesicle walls, the vesicle membranes that we're going to be looking at with XPCS, it's these sorts of fluctuations that we're looking at. So I think I can go on to the next slide, back to my PPT. And here, I don't have any fancy movies to show you in this case, because the movies from polymer systems would be rather tedious, because the number of scattered photons in each frame is very small, and you simply can't see the sorts of persistent speckles that I showed you in the context of the colloidal systems. So in this case, all we can do is calculate the correlation functions, but we do it in exactly the same way. And this is the intensity autocorrelation functions are shown over on the left-hand side, I should say, for a volume fraction of the tri-block copolymer of 3% at several different wave vectors and at a particular temperature here. Now it turns out that so previously I was describing the intensity autocorrelations when we fit them, we were describing them as simple exponentials. You can tease out from the data whether they're actually single exponentials by plotting the log of the intermediate scattering function. That's to say, we take G2, we subtract 1 from it, and then we take the square root, which gives us the intermediate scattering function. If we plot that on a log scale versus linear time, why then, if that is an exponential function, we expect to see a straight line. We've done that here, and what you can see is actually there's a little bit of curvature on these lines. And in fact, we fit these data to stretched exponentials, and the stretching exponent is a fitting parameter. And you can see, though, that the stretched exponential provides a pretty good description of these data at actually all different wave vectors. The reason that we're sort of happy about this result especially is that for individual membranes, there are detailed predictions for what we expect. Specifically, we expect that the intermediate scattering function f should in fact be a stretched exponential with a stretching exponent beta. This thing beta here is the stretching exponent, and that's predicted to be slightly larger than 2/3. If we fit it, this shows the results of those fits. It fits to about a value of about 0.8, sort of exactly as predicted. Well, slightly larger than 2/3, 0.8. I'm just going to say that they're the same thing. In addition, the characteristic rate that appears in the stretching exponent has a signature wave vector dependence q cubed, and if we normalize the measured values of gamma obtained from fitting the intermediate scattering function with the predicted values from this Zillman and Granick paper, then we find a value of 0.2 for the ratio. Reduced relaxation time is the measured value of this thing divided by kBT q cubed over eta, where eta is the viscosity of the polystyrene solution. And sort of amazingly, the prediction is 0.025, the measurement is 0.02. So it really seems like, in this case, we've been able to access these theoretical predictions for individual membranes in this rather messy system consisting of these vesicles. So that's these things. So at 160 degrees, these guys are fluctuating around in the way that that you saw in the movie. Things are not nearly so clear-cut, or I shouldn't say clear-cut, they're pretty clear-cut, but they're simply not understood in the case of the denser phase, where you have these many more membranes that interact with each other and interfere with each other. In this case, at high temperatures, 180 degrees, you see this. I'm plotting things in the same way: logarithmic scale along the y-axis, linear scale along the x-axis, and you see that these are very definitely not straight lines. So the stretching exponent is rather small, 0.2 or 0.3, something like this. This is at 180 degrees, but if you go to lower temperatures, 160 and 140, the stretching exponent gets less. And if you go even further, it becomes greater than 1. So it's no longer a stretching exponent; it's a compressing exponent. And I think I should wrap it up just to say that compressed exponential intermediate scattering functions, such as we're seeing at low temperatures in the context of this sponge phase, are associated with random strains and seem to actually to be very widespread in soft condensed matter systems. I'm going to skip that. Let me just sum up then. So I spoke about brightness, coherent X-ray beams, and XPCS. I hopefully convinced you that this is a method that can measure something in the context of colloidal suspensions. I then specialized to glass transitions in a colloidal suspension in which we could tune the interaction strength from nothing to some attractive interaction, and we got different glassy behavior in those cases. And then finally, I briefly mentioned about the dynamics of polymer membranes, which are also accessible with this technique. Finally, let me thank, I'm going to skip this, I'm going to skip this, and I'm just going to thank the folks who did this work. Sinwei Liu, who's now actually at the University of Hong Kong, the Chinese University of Hong Kong, made the measurements on the colloidal glasses. Peter Fallish, who's now a neutron scatter at ILL, made the measurements on the polymer system, and Michael Sprung, Alexandi, and Suresh Narayanan were also involved in the both of those measurements at the Beamline at the APS. Thanks to the NSF and the DOE for support over the years. I guess that's it. I'm done. Only 5 minutes over. Well, 6. Any questions? So the question is, what do you expect? What difference do you expect if the colloidal particles are not spherical? For example, if they're cylindrical. So, one definite possibility with cylindrical particles is that they might form a nematic phase where there's orientational long-range order. In that case, the scattering pattern, I think if you could get an oriented sample of such a phase, for example, you might be able to orient it using an electric field like in your watch or through some other means, then the scattering function would not be circularly symmetric necessarily, and you might be able to measure the time dependence of fluctuations in different directions parallel to the nematic order or perpendicular to the nematic order. So I think there's actually a lot of potentially very interesting experiments to do on those sorts of systems where there's more order than simple, unstructured, completely disordered liquids. So hopefully that answers the question. Any other questions? Otherwise, I'm going to say goodbye. Bye-bye.